Hello, are you able to see my screen?
Yes.
Okay. So I'm Yogesh Wadadekar, and I work at the National Center for Radio Astrophysics, which is in Pune in India. And today I'm going to be talking about big data challenges in radio astronomy, looking forward to the Square Kilometre Array Telescope. So the genesis of our participation in the BRICS program was in the form of this BRICS SKA proposal that we had submitted some years ago. And these are listed here, my Indian co-investigators. And this is a mix of radio astronomers from my own institution, the National Center for Radio Astrophysics, our neighboring institution, the Inter-University Center for Astronomy and Astrophysics, and Ramana from the Indian Institute of Science Education and Research. In my talk, I'm going to just focus on two aspects. One is a big data archive that we have developed for the GMRT, and about how we store and deliver data to the international user community, and more importantly, how we now process data to make it more science ready. In the spirit of what Russ mentioned earlier, data itself is not very useful. You have to do a lot of work in order to convert data to knowledge so that it can be used to inform our science. In the second part of my talk, I will talk about SK data delivery and processing using what are called the SK regional centers, and about the first baby steps that we are taking in the form of proto regional centers over the next few years. So the Giant Meter Wave Radio Telescope has maintained a data archive since the beginning of its public operations. So we have stored all interferometric observations made since 2002. And since GMRT has operated with an open sky policy since the beginning, the kind of observations that we have obtained correspond to the interest of the worldwide low frequency radio astronomy community, and therefore span a very large variety of science areas. Over the last 18 years, more than 500 PIs from 35 countries, including all the BRICS nations, have obtained their data with the GMRT. The data archive that we have contains about 250 terabytes of data, and it's growing rapidly at about 100 terabytes per year. It forms the largest public astronomy data archive in India. The data that we are currently serving to users are served as raw visibilities. So this is the Fourier transform of the intensity of the sky. So these are the observations as they are taken with a radio interferometer. And these are accessible to users via a searchable web interface, which we call NAPS. Here are the colored in green are the countries from which the GMRT archive users come. And of course, that includes all the BRICS nations. Certainly China, India, and South Africa have been heavy users of the telescope. We've had somewhat fewer users from Russia and Brazil. The GMRT observations over the last 18 years do cover a wide part of the sky. What you see here are the number of observations that have been made for different parts of the sky with the GMRT at just one of its bands, which is the 325 megahertz, the P band of the GMRT. Of course, all the other 4 bands have also been heavily used, and there are lots, literally thousands and thousands of observations that are now available. So as was mentioned earlier, big data is useful only if it can be converted easily into information, which can then be analyzed by the scientists, which then eventually produces the scientific knowledge and insight. This is a major problem for all radio astronomy facilities that are now operating, because data volumes have become so large that the traditional analysis techniques, where the users would simply download the raw visibilities to their desktops and spend a long time obtaining an image or a spectral data cube, is no longer feasible. So we need basically to move on and basically automate this process and help the users out by taking the raw data and converting it into more useful information that they can analyze. So some years ago, we decided that for the GMRT, we should have a program that takes all the GMRT archival observations that have been made over the last 2 decades and process them through an automated pipeline and deliver continuum images. We are just working with the images at the present time. The spectra, which correspond to the line data, will come in the future. And so we have a project called the GMRT Archive Processing Project, which is dedicated to this effort. We're now processing 1 GMRT cycle at a time, and we generate images for every continuum observation in that cycle. And this, of course, as I mentioned earlier, the GMRT is a broad radio facility that enables science in a variety of areas. So naturally, the observations will give us images that enable a lot of different science. So this is an image of a supernova remnant in the 4th quadrant of our galaxy. The foreground image is from our project, from the GMRT, and in the background you see the rich stellar field. This is made from a TUMAS image. And of course, the supernova remnants lie within the disk of our galaxy. So very often you have very, very dense, high density stellar fields in the background. There are a number of nearby galaxies that have been observed in the radio with the GMRT. This is an example of an image of M51. On the left-hand side, you have the from the image from the Sloan survey. And on the right, you have an image of the same part of the same galaxy made with the GMRT. Radio galaxies are detected in their thousands in large radio surveys. And the GMRT has been used over the years for observations for a subset of those. And this is an observation of a radio galaxy made with the 610 megahertz band with the Pan-STARRS image in the background. Galaxy clusters. So this is in the foreground is the GMRT image processed through the gap processing. And in the background is an HST I-band image for context. This is a pair of, not a pair, there are 4 merging clusters at a redshift of 0.55, which create these very large extended radio emission. We refer to them as radio relics. And what you see here is quite appropriately called the armchair relic. Deep fields are also a topic of great interest for radio astronomers these days, and well-known fields that have been observed in other wave bands like the Lockman hole have also been imaged to quite good depths with the GMRT. And this is again an image that has been produced with our processing. So we've started public release of all the images that we are producing. These images have been integrated into the GMRT online archive, which is a component of the NAP system. And so far we have released about 4,000 images from 10 cycles, which represent in total about 5 years worth of observations. So although we've made a lot of progress with the GMRT, the challenges in the SKA era will be totally out of in a different class. The SKA phase 1 will generate about 700 petabytes per year from the 2 telescopes. And this enormous amount of data has to be stored, it has to be distributed, and this data has to be looked at by the scientists and analyzed. Naturally, traditional user-based, desktop-based analysis will simply not work. We need to move the storage close to the compute and have some sophisticated data visualization tools for remote analysis. Within the SKA, the mechanism envisaged for delivering science with the SKA data is via the SKA regional centers. So there are two telescopes, one in Australia, one in South Africa, each of which has its own science processing center. The outputs from the science processing center will be delivered to a number of regional centers. We don't know exactly how many at this moment. And each of those regional centers will cater to users, possibly within their region, but also they will be interconnected with each other so that they will share data amongst themselves. So when a user requests a piece of data, it may well be that part of the data will be fetched from multiple regional centers, but this will be transparent to the user because they will access the data through a common science portal, which is indicated by that line over there. Where will these regional centers be located? Okay, this is the putative layout for where the regional centers will be. So all the three nations that are currently members of, from BRICS, which are members of the SKA, India, China, and South Africa, all are expected to host a regional center. Each regional center will be connected both to the telescopes and to each other via a network of high-speed optical fiber networks. And what will they do? The regional centers will provide access to computing resources, okay? They'll provide support for subject-specific pipelines. So there are a number of key science projects that are running within the SKA, led by different countries. So each regional center will support specific data processing pipelines that are required for the key science project in that region. They'll contribute to efforts in visualization and other software. They'll provide resources for SK simulations that will inform the use of the telescope. They'll provide access to data, and they'll provide some amount of user support, proposal access, training, and outreach activities in one coherent unit. They will also liaison with the SK observatories and with the national research and education networks to ensure that the required resources in terms of network capability is possible. Of course, this is all in the future when the telescope is ready. As a first step, one needs a prototype regional center, because at this scale, so all countries in the BRICS, India, China, and South Africa, have begun developing a limited version of the SK regional centers, what we call as a prototype SRC. The prototype SRC will be like a regular SRC in the variety of services that it provides. It will just have the smaller size and scale, not the same size. The plan is to build a prototype SRC over the next 4 to 5 years, and then build the full SRC in time for completion of the SK phase 1. There is a considerable effort in terms of FTE. Most countries in the SK project have committed of the order of 50 FTEs to work over the next several years to develop the SRCs across the world. Within the Indian SRC that we are proposing, we are basically taking a three-pronged approach. We want to develop and implement a data processing pipeline for the upgraded GMRT data, which is quite large. I mean, it's producing now upwards of 100 terabytes a year. We want to develop and implement a pipeline for processing other precursor data from telescopes like ASCAP, MeerKAT, and others. And we also want to develop large-scale computer simulations in various areas that are of relevance to the square kilometer array. We realize here that this will require collaboration not just between academic research organizations, but also with industry partners and with the National Education and Research Network, which will provide the backbone for transporting the big data that we are talking about. And all of these things we are beginning to do. Working with industry partners, we've done for many years, primarily because of our participation in developing the monitoring and control system for the GMRT. We look forward to collaboration with other proto SRCs in the BRICS collaboration. All SRCs face similar technical challenges. In fact, the challenges that will be faced by regional centers, data centers devoted, let's say, to the LSST project will be quite similar because of the high volumes of data involved and the challenges of making that data useful to users. So we look forward to extensive collaborations, so not just with other SRC efforts, but with other large big data centers in Russia and China and Brazil, who are not members of the SKA. Some proto SRC efforts have moved quite a bit forward. For example, in China, there is already a proto SRC which is ready and has invited collaboration, and efforts in India and South Africa are also underway. So that's it. I'll welcome your comments and questions.
Thanks very much, Yogesh. And thanks everyone actually for all of these great presentations. And I think given everything that's been discussed today, the fact that we're only about 15 minutes over time, I think is testament to the fact that, yeah, that we've had a lot to discuss.